Okay, so we're looking at absolute value functions, and so the previous questions that we did, 1 through 3, we looked at given a function, take the absolute value of it. You read this, these are the absolute value functions, so we need to go back and figure out what the original function was. So it says sketch the possible graphs. Notice how that's plural. So maybe there's more than one possible graph to start, and determine the equations of them. So remember, given a function, when we take the absolute value, anything above the x-axis stays the same. Okay, when you take the absolute value of it, anything below gets reflected above. So if actually I'll use a line here. If I had this line as my f of x, and I took the absolute value of that, this would stay the same, which means it would be the black part that's already graphed here, and this would be reflected up. So this is a possible f of x. So here, this is a possible f of x. What's the equation of that? So remember back to math 10. So that's, well, I'll call it f of x, I guess. So f of x equals, so the y-intercept's -2. What's the slope? Down 1 to the right 2. So -1/2 x minus 2. Okay. That's one. What's another possible one? The other one. Yep. Yes, exactly. So basically the opposite if you multiply this by -1. All right, so here, and that would be if I drop that original, it would be like something like that. So this would be, sorry. F of x equals +1/2 x plus 2. Okay, so either of those are possible original graphs. Next one, again, if it has that kind of a W shape, then it's come from a parabola. So if we had a parabola that opens up to start, then these wouldn't change. I'm just going to minimize this a little bit. So these would be your original parts, and this would have been reflected from below. So that point here, x is 2, y is 2, would be x is 2, y is -2. So it would look something like that. Okay, so now what's the equation of that? Remember back to the quadratics. Actually, I'll call this f of x again. So this is going to be f of x equals, so the vertex is 2, -2. So x plus 2 squared minus 2. And what's the stretch factor? So normally for your base quadratic, 1 unit over is 1 up. Now 1 unit over is 2 up. So that's 2. You don't have to do it algebraically. Always remember that if I ask you to graph something, the original or the absolute value, make sure you graph over top of any lines that don't change. Don't just skip it out and say, oh, that's going to be part of it. I need to see your pencil. And if your pencil is really faint, then make it darker. Okay? If I can't see it, then I think that, yeah, maybe you're lazy, but I don't know. You know that that hasn't changed, right? So you need to make sure that you're expressing what you know. So what about if these parts here, this part here in the middle was the invariant part, okay? So that would be on the original. That means these would have been reflections. So these would have extended down like this, okay? Yep. Oh yeah, it would be. Thank you. Good. X minus 2. Oh, fix that open. X minus 2. Thank you. Because it's to the right. Okay, so that's got to be opposite sign there. I don't know why I put plus 2. No idea. Okay, so then let's do this one. So this is going to be f of x. Basically, it's the same parabola, same shape. Vertex is in a different location, so now it's x minus 2 squared plus 2. And it's opening down, same stretch factor, the size is the same. So this is going to be negative 2 out front. And again, really, it's the entire opposite sign of this one, right? If I multiply everything here by negative 1, I get negative 2, x minus 2 squared, plus 2. Okay, so it's a complete reflection. Okay, so that's question 4. Okay, question 5. Now we're given the absolute value. Inside is a linear function. Sketch the graph of the absolute value function by first sketching the inside function and then reflecting it. You can use your graphing calculator to verify if you need to. So it says by first sketching this. Okay, so I'm going to do that in blue, a different color. So remember back from Math 10, y-intercept of negative 3, slope of negative 3 over 2. So down 3 to the right 2. Do it a few times. Or you can go up 3 to the left 2. Do it a few times so that it's easy to join up with the straight edge. If you don't have a ruler, then remember, try your battery cover of your calculator if you have one that has actual batteries in it. A little bit off there. Better. Okay. So that's your original. Now I'll use red for the absolute value. So anything that was above stays. So this part here that's above stays above. Okay, this part below gets reflected. So here, choose a few points if you need to. So negative 3 for y becomes positive 3 for y. Negative 6 for y becomes positive 6. Negative 9 becomes positive 9. And then it should be pretty easy to join up with a straight edge. Okay, so from there up. Okay. I guess I can move this up. Okay, so state the intercepts. So, looking at the graph, the x-intercept is negative 2. So, x-intercept is negative 2. y-intercept is 3. Okay? If we look at the equation, x-intercept is when y is 0. Okay? We'd actually have to look at cases there, right? Because if we just look at the inside function, then, well, actually, it would work either way. To get the x-intercept, it's going to be -2 no matter what. Y-intercept, that's when x is 0. You have to have the absolute value. So here, this ends up being -3 inside, because that term goes away. Absolute value of -3 is +3. Okay? Domain and range for a linear absolute value that is oblique, okay, so not vertical or horizontal, then the domain is always going to be all real numbers, okay, because it's going to have the same domain as the line. You can put anything in for x. It's what you get out, the range, that depends what you put in, right? So here, our range is everything greater than or equal to 0. Okay? If we had, so for an oblique line, as I said, that's always going to be the case. If we had the domain and range of a quadratic, then it really depends. Did that quadratic even touch the x-axis? Maybe it was all above, so you're not going to have a y value of 0. You have to analyze what it looks like. So range is y greater than or equal to 0. So basically, in the absolute value function, if there's an x-intercept, your range is always going to be greater than or equal to 0. Okay, then piecewise functions. So this is something that you may not have learned before at all. So basically, piece, what is the word piece? P-I-E-C. Breaking it up into pieces. Okay, so we're breaking it up into pieces that don't require absolute value symbols. So think about the pieces that we have here. We have this part of the original line. So that's a piece of that original line. That red part is the original line for x less than or equal to -2. Then this part here is the reflection of this. If we multiply this by -1, we get that function there, but that's only defined for x greater than -2. So this x-intercept is really important in where we split it up into pieces. So how we show piecewise function, we kind of do a big squiggly bracket. I don't care how you're squiggly bracket if it's not that nice. I don't really care. We split it into the inside function, okay, and then the opposite sign of the inside function. And you can even show it like that without simplifying. I'm okay with that. Then at least I know exactly what you've done. Really, that's the same as +3/2x. So either that or +3/2x plus 3. Okay. As I said, I'm okay if you actually don't simplify the negatives. Those are your two pieces. They're not defined for all x. This is that, there's that graph of that function, is that whole blue line. We only want the red part. So that's for x less than or equal to -2. So you put a comma afterwards and state the domain, but not in all set brackets, just as an inequality for what values of x it is this. When we take the opposite of that, that's this line extended here, but obviously we don't want this part. We want everything to the right of -2. So this we'll have x greater than negative 2. And just put equals in one of these. Okay? I don't care which one. Right? Don't put them in both, because it's kind of saying it twice. I mean, it doesn't really matter because it's continuous. It's not like it's an open circle there. But you're leading up to negative 2 here, and then you're going to the right of 2, negative 2. Okay? That's a piecewise function. So you keep, for absolute value, you're going to do this for other functions as well, particularly when you get to calculus. And they're not necessarily going to be absolute value functions.
Can you put a line underneath it that the x is greater than negative 2?
Yeah, that's what I just said. One place or the other.
Okay, it can't be both.
Well, it's just not the best form. Yeah. So you can do piecewise for other functions, and you will, especially when you get to calculus. This is piecewise for an absolute value. And so just remember it as whatever's inside the absolute value is one of your pieces. It's not going to change. Then the opposite sign of what's inside the absolute value is your other one. Then you need to figure out for what values of x each one works. Obviously here, that's your x-intercept, right? That's the key. That's what's going to go in there, x-intercepts. Okay? Because anything below the x-intercept is negative, and that changes. So I think there's a quadratic in the next one. So it says, sketch the graph of that by first completing the following steps. So algebraically determine the intercepts of the original parabola. Okay, so y-intercept's easy. That's when x equals 0. So y-intercept equals negative 3. And x-intercepts, that's when y equals 0. So 0 equals 2x squared minus 5x minus 3. And factor that. Okay, so here, two numbers that multiply to negative 6 add to negative 5. So that's going to be negative 6 and positive 1. Okay, so then x is negative 1/2 and positive 3. Then algebraically determine the coordinates of the vertex. So you decide how you want to do that. Really, if you found the x-intercepts, then you could find the axis of symmetry. That's the x value at your vertex and substitute it in. Or you could complete the square on it. So you decide what you're going to do. Okay, so if you decide that you want to complete the square, then remember you factor out the 2. And then take half of 5 over 2, 5 over 4, and square it. So 25 over 16 minus 25 over 16. If you wanted to find the axis of symmetry, that method, so multiply by 2, so negative 1 plus 6, 5/4. And then you want to find y when x is 5/4. Okay, so you get the same thing either way. All right, so totally up to you. The method of finding the axis of symmetry and then substituting in, you actually have to deal with decimals or fractions a little bit more. Completing the square, that's a method that we've been using. We've used a lot, right? So totally up to you. It says use the intercepts and vertex to sketch the graph, because these aren't like totally nice numbers, right? So this is going to help a little bit. So our intercepts are nice, negative, well, pretty nice, -1/2, 3. And our y-intercept was, what was it, -3, I think? Yeah. Okay. Then our vertex is 5/4, so that's 1 1/4, and -49/8, so that's -6 1/8. So about there. Okay, and then so that's your axis of symmetry, right? So it's equal on either side of that. You can even do something like that. For your axis of symmetry to help you out. And then so that's 1 1/4. So 1 1/4 is equal on the other side would be about there. That's equal on that side, and that's really pretty close to enough. We've got 5 points. Really, for a parabola, you should plot 5 points. Okay. You could even test out, that looks like it's 2. Actually, we know the stretch factor is 2. So for 1 unit over there, it's going to be 2 up. So I'm a little bit off, but not too bad. Okay. So from there, now we want to graph the absolute value of that. So anything above stays the same. So this stays, this stays, and these get reflected. So if I've drawn that line, it actually is a little bit helpful. This is going to be a little bit more than 6. This is going to be +3. This is going to be +3. And so now we can join there. And that there. Graphing calculator. I got a better one loaded, but I still have to, it's easier to do it here. So, y equals, remember absolute value is math key, num key, absolute value. So, yours will likely have those vertical lines. An older version will have the letters ABS. Okay, and then we're going to enter 2x squared minus 5x minus 3. And then window, what is the grid that we have here? We have basically -2 to 4 and -7. Oh, sorry, clear on that. Going up by ones. And then -7 to +8. Going up by ones, and you can graph that. Okay, it's spread out more, it looks wider, because when we gave you this scale that we have, goes from -2 to 4, but it's skinnier, right? If we compress that, that's really a rectangle. Your screen is a rectangle, right? And this is going the other way. You can test some values. So if you go trace, go 0, 0 for x, you should get a y-intercept of 3, which we did. Okay. we've got 3 for x. We should have 0 for y. You could test more points. It looks like it goes through 2, 5. 2, 5. That was pretty good then. That does go through 2, 5. All right. So you can test some points. Okay. State the domain and range of the absolute value function. You can put anything in. Okay. What you can't put in would depend if you say you had a radical inside the absolute value or something like that. But if this is a polynomial function, put any value of x in. What's going to come out depends on the shape of what goes in. If this crosses the x-axis, that blue, it does, then the range of the absolute value function will be everything greater than or equal to 0. The exception for that would be if you had a graph, say that had a vertex here going up, and I were taking the absolute value of it, it's not going to change. So the range starting is going to be the same as the range of the absolute value. Here, if we had something opening down, we take the absolute value, then the range here, so if we take the absolute value, it's going to be up at 2 going up. So our range would be y greater than or equal to 2. So it's only greater than or equal to 0 if it crosses, the original crosses the x-axis. Which most of them do, that we are doing, but certainly not everything. Okay, then piecewise. So y equals, squiggly brackets, takes 2 lines. First, I always put in the original. It's the easiest. And the second one, I change the sign. So, negative 2x squared plus 5x plus 3. Okay, or you can go negative bracket 2x squared minus 5x minus 3. You've got to multiply through every term by that negative. All right. So now, for the absolute value function, which is red, okay, where is it equal to the original? So where is the red and the blue the same? So they are on these arms here. I'm just going to erase this just to get them more crowded. So where is the red and the blue the same? That's for x less than or equal to negative 1, greater than or equal to 3. Okay. You can use a comma or the word or. Or actually the word, the letter union as well. Oh, right. Sorry. Negative 1/2. Thank you. Just checking to see if you're yeah, that was my mistake. So here, this point here is at negative 1/2. I just was quickly looking there. Yeah, good stuff. So negative 1/2 greater than or equal to 3. So those are your x-intercepts that we found up there. Okay, I included the equals. If you don't, that's fine, but you're going to include them in the next one. Okay, so the next, where did we actually have to reflect? So this absolute value is the red. We had to reflect all of these points here. What are the x values of those points? They're everything in between this. So if I've included the equal signs there, then I don't include them here. Or if I include them here, I don't include them here. Okay, so overall, this will be all real numbers. Because this is everything up to including negative 1/2, then from negative 1/2 to 3, and then from 3 to infinity. Okay. So that's kind of why we did it in that order. Find your x-intercepts first, so that's going to help us with our piecewise function there. And that's it. Okay.